From 747 kilometers above Earth, a satellite can detect ground that is creeping by only a few millimeters a year.
Not a city sliding across a map, not a mountain visibly collapsing, a movement smaller than the width of your fingernail. And it does not measure that by taking a sharper photograph. A radar satellite sends microwave pulses toward Earth and records the echoes that return. Because it supplies its own signal, it can work in darkness, and its longer wavelengths can observe through most weather clouds. The strength of each echo helps form an image, but the satellite is also preserving something ordinary photographs do not contain: the phase of the returning wave. There is one engineering inconvenience. A radar antenna large enough to make a very sharp image from orbit would be inconveniently enormous. So the satellite uses motion instead. As it travels along its orbit, it observes the same patch of ground from many positions. Processing combines those measurements as though they came from one much larger antenna. That imaginary giant is the synthetic aperture.
Two radar images of the same landscape can look almost identical.
Excellent. The mountain remains mountain-shaped, but the useful clue is hidden inside the wave.
Imagine each radar wave as a repeating cycle. When the echo returns, its phase tells us where it arrived within that cycle. If the ground moves slightly toward or away from the satellite, the round-trip distance changes. The next echo returns at a slightly different point in its cycle. The surface may look unchanged, yet the phase of the returning radar wave has shifted.
For that comparison to mean anything, the satellite must return with nearly the same viewing geometry. NISAR repeats its orbit every 12 days.
The two radar images are then aligned pixel by pixel, so a building, rock face, or stable patch of ground is compared with the same target from the earlier pass.
Even a tiny misalignment can manufacture a difference that never happened.
Now the two-phase measurements are combined. Where the waves reinforce or cancel differently, the comparison produces an interferogram, repeating colored fringes across the landscape.
The ground has not become decorative.
Each complete color cycle represents a known change in the radar wave's round-trip path. Closely packed fringes indicate a sharper change. Wide spacing suggests gentler movement, all measured along the radar's line of sight.
But a colorful fringe is not automatically ground definition.
Topography changes the travel distance. A slightly different orbit changes it. The atmosphere and ionosphere can delay the signal, while vegetation, water, or surface disturbance may change the scattering pattern itself. Scientists model or remove these effects, check whether the signal stayed coherent, and often compare many observations over time before trusting the motion. NISAR carries two radar wavelengths. Its 24-centimeter L-band signal can penetrate farther through vegetation and interact more with larger branches, trunks, and the ground beneath. Its shorter 9.4-centimeter S-band signal interacts differently with vegetation and surface structures, adding complementary information. From its science orbit, NISAR's repeat-pass L-band interferograms can be sensitive to large-scale deformation rates as small as 4 millimeters per year.
That is a processed, repeated measurement, not a one-pass promise for every pixel on Earth. In July 2026, NISAR began continuously releasing calibrated L-band products, while ISRO released operational S-band products through its own portal.
Those repeated measurements can reveal displacement after earthquakes, the slow creep of landslides, sinking caused by groundwater withdrawal, and the motion of glaciers and ice sheets.
So the satellite does not need to watch a crack open. It sends a wave down, measures the journey back, returns later, and asks whether that journey changed. A flow length becomes an invisible ruler for a moving planet.